I will explain you continuity of measure. This is a proposition that you can see in the 5th unit of measure and integration. So here you can see the statement of this proposition. So let x comma script m comma mu be a measure space. They are given you a measure space. Here x denotes a set, okay. Script m denotes subset of x. Is that clear? Now mu means it denotes measure. You are denoting measure using this mu. Is that clear? So yeah, they are saying this is a measure space. A measure space is given to you, and by giving that they are asking us to prove these two conditions. The first condition is if collection ak k equal to 1 to infinity is an ascending sequence of measurable sets. They are saying this is an ascending sequence. We all know what is called ascending sequence. What is called ascending sequence? It is from small to big, right? So it means they are saying this ak k equal to 1 to infinity is an ascending sequence of measurable sets. It means a1, a2, a3 till a infinitive. They are measurable sets and they are arranged in an ascending order. It means here you will have a1, okay, one of the measurable sets. This is a1, consider, and this is a2, and this is a3, and this is a4 till you will have infinitive. Okay, so here when you look at this a1, this is smaller than a2 and a2 is smaller than a3. Okay, it is an ascending sequence of measurable sets. This is how these measurable sets are arranged in an ascending order. Okay, so here if ak is an ascending sequence of measurable sets, you have to prove this equal to this. And similarly they are given you second condition also. In second conditions they are given you a sequence, that is b k equal to 1 to infinity, and this is also measurable sets and they are arranged in a descending order. It means you will have b1, this is b1, and b2 will be present inside this because b2 is smaller than b1 because they are arranged in a descending sequence, and you will have b3 till you will have b infinitive. Okay, this is how this b collection bkk equal to 1 to infinitive is arranged in a descending order. Now for which another condition is also given, mu of b1 is less than infinitive. What is mean by this? When you find out the measure of this measurable set b1, the value will be finite. That is what the meaning of this. Mu of b1, the measure of b1 will be finite. That is what the meaning of this. Then if these two conditions are there, then we have to prove this. This is what our statement. Now let us prove the first one. Okay, so the first one, you are going to prove this using two cases. Let us see the case 1. Okay, in case 1 you have to consider mu of ak naught equal to infinitive for some k naught. It means you are taking some any one of the measurable sets from this collection. Okay, that is ak naught, and you are saying measure of this ak naught is infinite. Equal to infinity means what? Measure of this measurable set is what? Infinite for some k naught. For some k naught means what? Some measurable set from this collection. Okay, so this is what our case 1. So from this we have, okay, not from this, we have, you have to know this, that is union k equal to 1 to infinity ak contains, what is mean by this? It's contains, okay, contains ak naught. What is mean by this? This is obvious. Is that clear? How I can say that? Here you are having union of all the measurable sets, a1, a2, a3, a4, etc. up to a infinitive. Okay, you will have all the measurable sets, and that's union is this contains AK naught. So AK naught will be present inside this union, right? Right, AK naught is any one of the measurable set from this collection. Is that right? So in this union, you will have this AK naught. Within this union, you will have this AK naught. So that is what you are writing like this. Union K equal to 1 to infinitive AK contains AK naught. That is what the meaning. Okay, this AK naught present inside this union. That is what the meaning for this. And then you are taking measure on both sides. When you take measure of this, how you are getting greater than or equal to? I will tell you, it is clearly here you are having measurable sets from 1 to A1 to A infinitive. So when taking measure for this will be greater than or equal to this, because here you have only one measurable set. Here you are having union of measurable sets. So when taking measure for this, that will be greater than or equal to the measure of this, right? So that is what you are writing. And here mu of AK not equal to infinity, because in case 1 you have took like that, you are using that here. Now from this line, comparing this two, you can write this and mark it as equation number 1. And next what you are taking as, suppose K greater than or equal to K naught. Okay, you are taking like that. If K greater than or equal to K naught means AK contains AK naught. What is mean by this? Because K is greater than or equal to K naught, right? So this is greater. So AK contains AK naught, because this is greater, no? So within this AK you will have AK naught. That is what you are writing. AK contains AK naught. That is what the meaning. What is the meaning? This AK naught present inside this AK. The reason is because you are taking K greater than or equal to K naught. K is bigger. So AK, this measurable set AK contains this. It means this measurable set present inside this AK. Is that clear? Now you are taking measure of AK will be greater than or equal to measure of AK naught, because the reason is because here K greater than or equal to K naught, right? So K is greater, so AK is greater. So when you take the measure for this greater measurable set, what will happen? The measure of this will be greater than or equal to measure of this. You are taken that mu of AK not equal to infinitive, so just you have write that. You have to write this, and then from this line comparing these two, you can write this for all K greater than or equal to K naught. Okay, now taking limit K tends to infinitive on both sides, so that you are taking limit K tends to infinitive and write this. And here you are not putting limit K tends to infinity. The reason is because in the right hand side you are not having any term with K, right? So you don't want to take limit K tends to infinitive. There is no need, because there is no any K terms to substitute limit K tends to infinitive. So that is why you are just putting infinitive here. Now from 1 and mark this as equation number 2. So from 1 and 2 you can write this equal to infinitive, and infinitive. This is also the value of infinitive, right? This is also the value of infinitive. This equal to infinitive and this equal to infinitive. So from 1 and 2 you can write like this. Write this first and then put this infinitive and equal to, and then write this. So from this line you can write the value of this also infinitive and value of this is also infinitive. So from this line you can write this equal to this. So you have proved what they have asked us to prove in the statement. You have proved it. Okay. So case 2 I will explain in the next video, because the video is very lengthy. It takes if the video is too much lengthy, then what the problem is, it takes too much of time to upload this video. Okay, so I don't want that to happen. I will upload case 2 of this proposition in the next video. Okay, you can go and check out my measure and integration playlist.